Hello. Um, it's time to get down to some actual maths instead of just the introductory spiel that I gave in the previous video. Um, so I want to start very gently with a result that will seem almost too easy to be worth mentioning. And basically that's the result that if you've got a random variable that takes real values, then with positive probability it will be at least as big as its average, and also by the same token, with positive probability, it would be at least as small as its average. So let me just write down exactly what I mean here. So and I apologize in advance for any technical glitches that there might be. But so here's the result. Here we've got a random variable x, and the statement I want to prove is that the probability that x is greater than or equal to the mean of x is positive. Now, actually, when x is a discrete random variable, this is really almost trivial. I can just say it out loud, I think, which is that if not, then the only values that x takes will be strictly smaller than the expectation, and at least one of those values is held with positive probability, and therefore, when you take the average, it must be strictly less than the expectation, which contradicts the assumption. So in the discrete case, it really is more or less a triviality, but I think it's worth just showing how to prove it in the sort of general, in the continuous case, because there it's not quite as trivial. It's sort of pretty simple, but it's not quite as trivial. So let's again suppose that the probability that x is at least the average is actually equal to 0. So what you're tempted to say is, well, then x is always strictly less than the average. So contradiction, because when you average over x, it must also be strictly less than the average. But that's the thing that's very, very slightly tricky to make work. So what we do is a little trick like this. Let's write, say, Pn equals the probability that the average of x minus 1 over n is less than x is less than or equal to the average of x minus 1 over n plus 1. So that's slightly bigger than that. So we know that, so x, remember, is a real valued random variable. All the values that it takes are smaller than the average. I'm going to go from 0. So when n is 0, this I take to be minus infinity. So whatever value x takes, I mean, with probability 1, x is going to take a value inside one of these intervals between ex minus 1 over n and ex minus 1 over n plus 1 for some non-negative integer n. So that gives us that the sum n equals 0 to infinity of these pn's equals 1. And therefore, there exists an n such that Pn is greater than 0. So now let's just look at what the average actually is. Well, we can get that the average, remember we're going for a contradiction here, the average is at most the sum n equals 0 to infinity times Pn times the largest it can be if x lies in this interval, which is ex minus 1 over n plus 1. And now if I look at this sum here, this part of the sum just gives me ex. So this equals ex minus sum n equals 0 to infinity Pn over n plus 1. And since at least one Pn is greater than 0, that bit is strictly bigger than 0, so this is less than Ex, and we had an Ex there, so that's a contradiction. So by a fairly standard trick of splitting things up into intervals, using properties of Lebesgue measure here, using the fact that the set of values such that x is in this interval will be a measurable set and that kind of thing. So secretly I've been using the Lebesgue measure, but let's not worry too much about that, because we're not actually in the course going to use the continuous case, but I just thought it'd be fun to show it. Now, actually, well, before I go any further, let me just say that since we've got that, we also have that the probability that x is less than or equal to its average is greater than 0. But the really surprising thing is that this extremely basic fact is also an extremely useful fact in combinatorics. And the way it's normally used is to say that we just to deduce from this, there exists or a value of x, let's say x less than or equal to, or I can change what I want to say there. That's true in a discrete case. Let me just get rid of that. In a discrete case, the way we use it is to say that there must be a positive probability that, so if there's a positive probability that x is at most its mean, then it must be possible for x to be at most its mean. And similarly, if there's a positive probability that x is at least its mean, then it must be possible for x to be at least its mean. And actually, sorry, that does work just as well in a continuous case. It is possible that x is at most its mean, and it is possible that x is at least its mean. So that seems extremely basic, but it is extremely useful. And we'll see some uses of that soon. But before we get on to using this principle, I also want to talk about another very basic principle that goes under the name of averaging arguments. So what I've just talked about is sometimes referred to when, or applications of what I've just talked about are sometimes called averaging arguments, but something else is another nice averaging argument. So I want to illustrate this with an example and then talk slightly more generally about what I'm doing. So let's consider the following question. It's a very basic question. How many edges does an icosahedron have? Now I'm going to assume that you might think, well, that's a little bit tedious if we draw a picture and we've got an edge here, and that's rather annoying. We don't really want to sort of think too hard about it. But there's a trick we can use. What facts do we know about an icosahedron? We know that it's got 20 faces, and that those faces are triangles. So we then reason that each face has 3 edges, and each edge is part of 2 faces. And what do we conclude from that? We conclude that twice the number of edges is 3 times the number of faces. And so the number of edges is 3f over 2. And since the number of faces was 20, that's 30. There are 30 edges in an icosahedron. Now, sometimes it takes a little bit of you have to sort of scratch your head and think, why was 2e equal to 3f? Was it 3 equal to 2f or whatever it was? So a nice way of thinking about this is to say that 2e and 3f are both counting something, namely the number of edge-face pairs where an edge is contained in a face. So an edge-face pair would be something like this. It's a face together with a marking of one of its edges. So how many of those are there? Well, each face contributes 3 edge-face pairs, and each edge contributes 2 edge-face pairs. And so 2e equals 3f, that's where that comes from. Now, This is actually a special case of a much more general phenomenon, namely, which is a statement about bipartite graphs. So another way of making exactly the same point about edge-face pairs, if I can get this to give me a new page, which I'm having trouble doing. Oh, yes, maybe it's over here. Thank you. So I've now got a nice new page. So let's take a bipartite graph with vertex sets x and y. And let's suppose that the degree of every vertex in x, so I've denoted it by little x, is always d1, and d of y, the degree of every vertex in y, is d2 for all y in y. Then what do we deduce from that? Well, we get that the number of edges we can count it in two different ways. So this is what I'm talking about is a sort of abstraction of the notion of double counting. So the number of edges is both d1 times the number of vertices in x, and it's also d2 times the number of vertices in y, from which we can deduce whatever we like. We can deduce that the size of x is equal to d2 times the size of y divided by d1, or if we prefer y, the size of y is d1x over d2. Now let's just go back and have a look at this icosahedron. We can see that's exactly what we did in the case of the icosahedron. We defined a bipartite graph, and the vertices on one side were the edges of the icosahedron, and the vertices on the other side were the faces of the icosahedron, and we joined an edge to a face if the edge is part of that face. And then here we were counting the edges in two different ways. So this is just an abstraction of that argument. And there's actually something else that we can do here, which is also nice, which is supposing we don't have equality here, we just have that the degree of x is always at most d1, and the degree of y is at least d2, then we get that the number of edges is, well, I better write a new thing down here, so that this is no longer valid, but we get that if the degree of every vertex is at most d1, then the largest that the number of edges could be is d1 times the size of x. And if every vertex in y has degree at least d2, then the smallest that the number of edges could possibly be is d2 times the size of y. And then we'll get from that that y has size at most d1 times the size of x over d2. So as I say, forget this line for now that I've changed those equalities to inequalities. If we've got inequalities, we can get, by a similar process of double counting, we can get inequalities relating the sizes of the vertex sets. Let me give an example of an application of that. It's a very, it's quite a useful fact, quite straightforward. So let us denote by, first of all, square brackets n is just a set 1, 2, up to n. And I'll write n r is the collection of subsets of n of size r. And now I'm going to take something, I'm going to take a nice interesting example of a set system or an R uniform hypergraph, by which I just mean some subset of nr. So what is a subset of nr? Well, nr is a collection of all sets of size r. So a subset of that is just a collection of sets of size r, about which we know nothing except that everything in here is a set of size r. Now I want to define a little notion. Let's suppose that S is greater than R. I'm going to define the upper shadow, or the S upper shadow of A is the set of B in NS, sometimes known as the S layer, such that there is some A in A with A being a subset of B. So saying it more colloquially, the upper shadow of A is everything in the S layer that contains something in curly A. And now let's think about, we would like to get some kind of bound on how large or small the upper shadow can be. I'm going to get a lower bound on the size of the upper shadow. So how am I going to do that? I'm going to say, let's join A in A to B in, I'll call it B, so that's just a little name for the upper shadow, if and only if A is a subset of B. Obvious thing that one would, obvious bipartite graph to define. What information do we have? Well, what is the degree of A if A is an element of curly A? Well, each set A is a set of size R, and we're just asking how many sets of size S contain a set of size R. Well, you've got n minus R elements to choose from, and the number of elements you need to choose, if you know that you've chosen, so yeah, what I'm saying is we've chosen the set A, but we want to extend it to a set B of size S. So R of the elements of B have been fixed. We've got n minus R other possible elements to choose from, and we need to choose S minus R of those. And that's true for all A in curly A. And what do we know about the degree of B? Well, given a set B, we know that it is at most the number of subsets of B of size S. So another of size R. So it's at most S choose R for all B in B. So the number of edges in this bipartite graph is curly A times n minus R S minus R equals the number of edges. And that's at most S choose R times the size of B. And that's got us the inequality we want. We get that the size of B is at least the size of A times n minus R S minus R over SR. And if you want to do a few little easy sums, you'll find that that's equal to A n choose S over n choose R. And notice that if A is the whole of NR, then we get an equality there. Right, that's not the sharpest bound that you can obtain. There's a famous theorem called the Kruskal-Catener theorem, which I'm not doing in this course, but I will just mention it. So if you want to know sharp bounds on how big or how small curly B can be given the size of curly A, then the Kruskal-Catener theorem is what you need to look at. Right. Let's get another page up. So I'm not going to say too much more in this lecture, but I will give an example of some more averaging arguments and double counting. And in particular, I want to talk about a result that's going to be needed for another result later on in the course, which is a nice illustration of these quite simple methods that I'm talking about today. So But before I do that, I need to prepare for it a little bit. I'm going to talk first of all about, so this is, what I'm going to talk about now is probably revision for most people, but nevertheless, I think it's good just to do it for the sake of completeness. So the first thing I'm going to just remind you of the definition of a tree. That's a connected acyclic graph. So it's a graph where you can get from any vertex to any other vertex by going along some path of edges, and there's no cycle. You can't go around from a vertex to itself without going over the same edge twice. And a basic fact about trees is that each tree has a tree with n vertices has n minus 1 edges. Let's just quickly see why that's the case. So the first claim is that a tree has a vertex of degree 1. So why does a tree necessarily have a vertex of degree 1, assuming that the number of vertices is at least 2, I suppose? It's because, supposing every vertex had degree at least 2, let's take a vertex, let's go to a neighbor. That vertex has degree at least 2, so it's got another neighbor. That vertex has degree at least 2, so it's got another neighbor, and you keep going. I'm assuming, by the way, of course, that the number of vertices is finite, and at some point, because the number of vertices is finite, you've got to go back to somewhere where you've been before, and lo and behold, you have a cycle. So that was just to remind you of proof that there exists a vertex of degree 1. And now I want to prove that there are n minus 1 edges, and we can do that by induction at this point. We just pick a vertex of degree 1, that's joined to the rest of the tree. Let's just remove that vertex. What have I got left? I've got n minus 2 vertices. By induction, sorry, I've got n minus 1 vertices, I beg your pardon. By induction, I've got n minus 2 edges. Then I put back this edge, and I've got n minus 1 edges. And of course, the induction starts. When n is 1, there are no edges. So that's the result, that every tree has n minus 1 edges. Next result, it's Euler's formula. That's the famous result that, well, it's normally stated in terms of polyhedra of a certain kind, but I think the version that we like in graph theory is, if G is a connected graph with V vertices, E edges, and F faces, and I've missed out a very important word, connected planar graph, then V minus E plus F equals 2. I want to say a little word about what F actually means. What is a face? A face is just a component of the complement of the graph when it's drawn in the plane. So if I draw, let's say this, then I'll say that the number of faces is 1, 2, and then an outside face, 3. So I've just put dots in the 3 faces. Right, so let's see how to prove this. First of all, we say, I'm going to prove it by induction. So my base case is not going to be quite what you expect. My base case is going to be the case where G is a tree. So proof. If G is a tree, so that is connected, it's planar, and so how many vertices have we got? We have V vertices. How many edges have we got? By the result we just talked about, we have V minus 1 edges. And how many faces are there? Well, you can get from any point in the complement of a tree to any other point, so there's only one face, and that does indeed equal 2. What about if G is not a tree? So then G, it's connected, so it can't be acyclic by the definition of a tree. So then G contains a cycle. So let's just draw something. There's our cycle, and it's got some other stuff. Let's try to make it look reasonably general. And now remove an edge from the cycle. Well, not from the cycle, let's say from a cycle. So if I do that, I get rid of this edge, let's say. When I've done that, what's happened? Well, because it was in a cycle, the graph remains connected. And I've removed that edge. Because I've removed an edge, I've managed to join two faces together, or in other words, I've reduced the number of components of the complement by 1. So that says V stays the same, and E and F go down by 1. So V minus E minus F, so V minus E plus F stays the same. And we're done, because we can just keep removing edges from cycles until we're down to a connected acyclic graph, which is a tree, and we know the result is true for a tree. So we're done by induction. Now, why was I doing that? It's because I wanted to prove one result based on that, which will be useful later on, which is, so let's write it as a corollary. It is that the number of edges, under the same hypotheses, we've got a planar graph. The number of edges is less than or equal to 3 times the number of vertices minus 6. So let's see why that's the case. So first of all, let's just compare edges and faces. So each edge is in less than or equal to 2 faces, and each face contains at least 3 edges, from which we get that the number of edges is greater than or equal to 3 times the number of faces over 2. So twice the number of edges is equal to, twice the number of edges is at least the number of edge-face pairs, which is at least 3 times the number of faces. Or equivalently, and more usefully actually for us, that F is at most 2e over 3. So we get that 2 equals V minus E plus F. And because F is less than or equal to 2e over 3, that's less than or equal to V minus E over 3. And then rearranging, we can get that E is less than or equal to 3V minus 6 as claimed. Actually, that was true for the connected ones, and then we can, it's easy to check from that it's true for non-connected graphs as well. So I think I'm going to leave things there. As I said in the introduction, I'm trying to make these lectures these videos not too long, so a lecture is technically more than one video. In the next lecture, we're going to get on to some slightly sort of deeper results, but still using quite simple techniques. So see you in the next video.